Okay, so hi everybody. Thank you so much for joining us for this week's online SEDS Online webinar. My name is Chelsea Pedersen, if we haven't had the pleasure of meeting yet, and I'm coming from University of Bochum this week. So first off, we have some really exciting news for you. As you can see on the screen, as well as the message in the chat, SEDS Online is going to turn 1 next week on April 7th. So we're going to celebrate our first birthday by having our first ever SEDS Online Great Debate. And this event is going to feature the 4 scientists that you can see on the screen, coming from different perspectives, different locations, and specialties in sedimentology to discuss this question of, is the recent really the key to the past? And so we're going to have 2 people arguing for the motion and 2 people arguing against the motion. So it's really important also, we want to let you know that you will have a large role in the participation and how this great debate is going to go. So you can sort of stand up, so to say, and speak your part and sort of add your perspective to this debate. So make sure and check in with that. We're going to send more information and we're going to be promoting it through our, all of the websites and the Twitter site, everything like that. So you'll see a lot more about it. So just keep your eyes open. Same time as usual, 4 p.m. UK time, and same day, so next Wednesday. It's going to really just allow for, or what we want it to allow for, is the discussion of this specific topic from various perspectives in sort of an open and respectful atmosphere, but definitely some nice scientific arguments as well. So mark your calendars for the first SEDS Online Great Debate. And before we continue any further with today's webinar, I'd just also like to thank our sponsors, the IAS, which really just allows us to offer all of the resources free of charge. So make sure and take a look at the website and see everything that is available to the sedimentology community. And today we're very happy to welcome Dan Leheron, who's a professor of sedimentology at the University of Vienna. And Dan received his PhD with the University of Wales before doing a postdoc at Strasbourg University and becoming a geologist at Cambridge for a year. He then moved on to a lecturer position at the University of Hanover before heading to Royal Holloway University for 10 years prior to landing in Vienna. So Dan's research focuses on glacial geology and what can be learned from the sedimentary record of glaciers. Today he's going to talk to us about what a normal glacial sedimentary record might look like. And with that, Dan, I will ask you to please share your screen and give you the mic.
Right, so thanks everybody for turning up today. It's good to see some familiar faces coming into the room. Yeah, my aim today is to ask this simple question: what does a glacial deposit really look like? It sounds like a really obvious question to ask, but actually the answer is a bit more complicated. And to sort of set up the big debate that Chelsea mentioned a couple of minutes ago, there are elements I hope to show you that we can see in the Quaternary that don't appear in the ancient record. And there are things that we see in the ancient record that are really weird and unusual, and they really don't represent themselves at all well in the modern and Pleistocene successions. So my aim is to cover today aspects of the modern, the Pleistocene, going back into the late Paleozoic Ice Age, the Carboniferous Permian, into the Ordovician, the Ediacaran, and the Cryogenian. Have I bitten off more than I can chew? Well, let's find out. Okay. The first thing you see on the screen here is a fabulous dropstone. This is in about rocks of 600 million years old in China, in the Luotian formation. And obviously this is a nice thing that you can see produced through an iceberg, very nice. But we're going to start off at the really at the modern process, and we're going to look at under a glacier. We've been monitoring and looking at this glacier in the Alps in Austria for the last couple of years with some degree of detail. And the point is, we can only scratch the surface here. It's not meant to be a fully representative or fully detailed presentation. It's to give you hopefully an impression of what each of these glacial records looks like and what makes them interesting, unique, and perhaps surprising. Okay, there's a picture of an alien you can see here, and the reason is that if an alien was to come down on Earth from outer space and take back to the mothership or to his or her planet information, and was asked to by the leader to bring information about what a glacial deposit looks like, then perhaps they would have sampled only one of these glacial records. Okay, so this really combines very well with the idea of uniformitarianism and whether the present is the key to the past and vice versa. Okay, so very obviously we've got these things called glaciers, which are icy. Here is the Gapach Glacier in Austria. You can see that right in front of it here, there is a deposit called a diamicton. All that means is it's a muddy deposit with boulders in and sand, and these boulders have scratches on them. Scratches are produced by the glacier, under the glacier, and within the glacier as it moves down the valley. Okay, and going back to the relatively recent or historical past, you can go down this valley and see deposits laid down during the Little Ice Age in about 1851. And quite honestly, the deposits look very similar. There are lots of big blocks in there, it's muddy, there's maybe some stratification you can see, and you start to get the impression that these deposits are degrading because there are tree roots in there that are affecting the structure of the sediment. Okay, so this is the beautiful sections in Countertown, and this is what the glacier looks like that produces those sediments, and it's been retreating since 1851. And at the margins there's a great big lateral moraine, a big dump of diamicton. And what you can see in front of the glacier here is a meltwater stream. There are deposits to the left of it over here. And in front of us, there's a beautifully scratched and streamlined gneiss bedrock. And what we're going to do is I'm going to show you a little 3D model of this area to just explain a little bit what we see before going back into the ancient record. Okay, and this is a model that Lucas Eder and Christoph Kettler have produced in our department. And you may see that it sticks a little bit, but I'll stop it here. There is the glacier, and there is this fabulous scratched and striated bedrock. And if we play the video, then as it goes around, we can start to see from this kind of perspective, there are areas that are scratched bedrock, and there are areas which are sediment. That's the diamicton. And what we are trying to do is to see the rates of change here in terms of what happens to the sediment budgets, the rates of removal and redeposition and cannibalization. And we can start to do this when you've got drones and you start to have digital elevation models. You can subtract 1 year from the other and see what has been added and what has been removed. And in this picture, you can see hopefully that there are different colors. And the purple areas, the dark purple areas correspond to the glacier. This is the position it was in blue in 2019. And exactly 12 months later in 2020, you could see it's retreated quite a lot, and it's lost an awful lot of elevation. Other things that have lost elevation in this area are in front of the glacier, and they include this meltwater stream towards the top of the picture. There's some purple areas, and the stream has basically cut through and cannibalized and reworked sands and gravels. And also other bits over here, there's a little landslide that's caused this elevation loss, and that's basically built up some sediment behind it that's shown in green. So why am I showing you all of this stuff? Hopefully this will become very clear. We start to map things, we start to see the changes even over a 12-month period, which allow us to quantify how much of this sediment is likely to be preserved, if at all, in the rock record. And before people say, hold on, this is impossible, this will never get preserved because it's really high up in the Alps, you see very similar deep valleys which occur in the Carboniferous in Namibia, And yet, in the modern day desert, 300 million year old glacial deposits survive in a similar context. Okay, so this is the point. The point is that the rate of change here is dramatic. What gets preserved? Why does it get preserved? And what is representative in the rock record? That's what we're going to try and do in the next 3/4 of an hour. First of all, let's think about the marks that are left behind. We go from areas of high confidence in the modern back to areas of lower confidence, or in terms of our concepts, in terms of our models, when we go further back in time. Hence the great debate. We can also see that going back 12,000 years, we're pretty confident. We can see these scratches in Ontario that look exactly like the scratches and striations we see in the modern day Alps. Let's keep going back. How far can we push this? We can definitely push this back to 290 million years in this section in Adelaide. There's a siltstone here. It's the bedrock near Proterozoic siltstone near Adelaide. And these amazing glacial scratches produced through the Gondwana glaciation. But we don't have to stop there. We can keep going further back in time. And in the next few slides, I'll hopefully convince you of this. But our little alien, who's tasked with going back to his planet and telling his alien friends what a glacial deposit looks like, might also have stumbled across an outcrop like this. This happens to be in Norfolk in the UK, and these are big folds which are produced through bulldozing. As the ice in the Pleistocene came down over the North Sea, it bulldozed and folded and thrust this sediment. Okay, so this is something that also comes into play, the idea of soft sediment deformation and the role that this can play in our understanding of glacial processes. Our perception might also be something like this. We might see a Holocene sand and gravel deposit in Iceland, in this place is Solheimjökull in southern Iceland, and what you see is a fluvio-glacial deposit, sands and gravels laid down by rivers above and below. And then there's a diamicton produced under the glacier as it went across the region, and it squeezed the material down to produce these amazing sedimentary dikes. And it's really tough, and you kind of hammer away on this material, and it's really difficult to sample. This is just a flavor of what we might see in the modern and in the Pleistocene, just a small part of it. I could summarize the Quaternary as something like this. This doesn't mean that the Quaternary looks like the UK, but the Quaternary represents a bewildering amount of data. It represents the ability to map huge areas with high levels of confidence, with great confidence offshore, seismic data in geophysical surveys, as well as onshore, to map the limit of ice sheets, and to do this with really an impressive degree of resolution. So this is a snapshot of what you can do in the Quaternary, coming from the huge Brit Ice project that involved a lot of people in the UK in terms of glacial geomorphology, and that looks really nice. But when you go back into the ancient record, this is normally what you're confronted with, except when you're in a desert. So you're looking at vegetation, you're looking at metamorphism, the overprint of tectonics, and then subsequent erosion. So what is actually preserved in the record is a big question, and is it representative? Okay. Luckily, in between those trees, in between the fields, you do find outcrops, and you can find things like these beautiful striated clasts, these pebbles here with scratches on, and you can even find striated pavements of which look very similar to what we have in the modern record. Okay, so let's dive in at the deep end and go for the oldest deposits first. We'll start off in the Proterozoic and look at the Siderian. Why the Siderian? This is a period of time when there was the first major interval of banded ironstone deposition. So glaciation and banded ironstone deposition occurring together. And there are various deposits you can look at. This is an example of a mining core from South Africa in collaboration with Bertha Smith. And this mining core allows you to see the structure of this diamictite and to hopefully see whether there are patterns, whether the pebbles are oriented in a certain direction, if it tells you anything about the depositional process. So you can do clever things like this to try and work out which way the ice was flowing, perhaps, but that's way outside of the scope of my talk. Can take questions if people are interested later. You can look at the outcrops, which are much rarer in rocks of this age. Nice picture from Marie Busfield here. And again, in these incredibly old rocks, again, there's striations that you see on the surface. And this whole orange color that you see is telling us that we've got an awful lot of iron in this sediment. Okay, so we have clues, we have little hints coming through that there are glacial processes involved here, perhaps. Okay, the caveat is perhaps. Why perhaps? Well, we have to be extremely careful. And this, we had talked about the diamictons at the beginning and the firm or lithified equivalents, the diamictites. Well, we know that they can be of glacial origin, but they can also be produced through mass flows. And you can get these in extensional basins like this. So this simple model in ISLES 1993 does the job nicely. We've got an ice cap up here at the top. It might be supplying sediment, but ultimately the texture of that sediment doesn't record any glacial process. It records the mass flow, maybe a debris flow, maybe an ilistostrome, perhaps when it's reworked a little bit forward into a slightly more mature deposit like a turbidite. Okay, and that's really important because it's common for people to say, aha, I can see a diamictite in the ancient record, therefore my deposit is glacial. That's not a good idea for the following reasons, which I'll hopefully convince you of. You can also get very similar things in compressional regimes, so in fallen basins. And people like Marek Vendorf have done a great job in Central Africa, in Zambia, in the Copper Belt, in this region, in Katanga, looking at large-scale blocks. You can see here they're actually wedged between two thrust slices, and the idea is that basically this material develops through large-scale comminution as you have one thrust slice basically ramping up over the other, producing these deposits. And it's a rather unfortunate thing that these happen to be about the right age to be interpreted or misinterpreted as a glacial deposit. Okay, so these are two things to be very aware of. And in order to illustrate that best, I thought I'd show you some pictures from the Cryogenian. So we're moving up now. We're leaving behind these 2.2 billion year old deposits, and we're going right up through the stratigraphy, but we're still in the Precambrian. And what you can see is that in this plot in Spence et al. 2016, this State of the Science paper we did a few years ago, we plotted all these different ages which correspond to minimum, maximum, and depositional ages according to the way that they are perceived in the original reference, and the perceived context, and obviously the analytical technique in terms of you know what it really means. Rhenium osmium being a very fashionable and extremely useful technique in the Cryogenian. Lots of great advances from that, and the error bars. And basically, if you read the literature of the Cryogenian, there are generally assumed to be the Sturtian and Marinoan glaciation as discrete intervals, and one or two other glaciations. The Kaigas glaciation seems to have fallen out of favour in this regard. And for those of you that are interested, these are thought by some people to correspond to snowball Earth events. Okay, so we'll have a look at some deposits from one of these intervals from the Sturtian glaciation in North America. Starting off with the amazing sections in Death Valley. When you go to Death Valley, you have no vegetation. The outcrops are amazing, and you can go to places like the Silurian Hills, which have no Silurian deposits, but they are rumored to have become known as the Silurian Hills because of their comparisons that could be made with the Welsh outcrops, grey turbidite bearing deposits. And we're going to zoom in on this section down here. What you see is basically a series of rocks which are vertical, more or less. And on this geological map, we're going from the bottom at the south of the map to the top at the north of the map. And this is about 1.4 kilometers of stratigraphy that we logged over about 1 month in a lot of painful detail. And there are two things to take away from this. The first thing is it's striping, and the second thing is that the stripes have meaning. So you can see that there are, for example, in this dark blue interval, there's something called a megaclast diamictite, and there's a light blue interval called a boulder-bearing diamictite. And the spoiler alert is that these have very different characteristics. And you can even map big blocks like that in the field, which I'll show you in a minute. So how do you even develop a sequence that looks like that? And perhaps more importantly, what does it mean? What does it tell us about glaciation? All of this sequence is overlain by something called a cap carbonate. So most of the, or many of the Neoproterozoic glacial deposits are overlain by cap carbonates, which are typically laminated dollar stones at the base, and then they pass upwards into microbially dominated successions with stromatolites and thrombolites. And so you can see the contact there. I'll show you an example of one of these later. This is what they look like on the ground. And I'm going to give you some propaganda and say these are glacially sourced diamictites. Why do I say that? Well, we have some clues, and we can find beautiful drop stones in these deposits. So I'll come back to that in a minute. These glacially sourced diamictites consist of basically massive deposits which have lots of gneiss clasts and granite clasts inside, something like this, okay, and some schist perhaps. It's predominantly a deposit dominated by crystalline basement. Okay, that's the critical thing. And above this basement, below the glacial deposits, we find a lot of carbonates. And this is one of the interesting things about Neoproterozoic glacial deposits worldwide. We often have carbonates at the bottom, glacial deposits in the middle, and carbonates above. So we know what was immediately lying beneath these deposits. We see laminated siltstones and shales. These are vertical, so the picture is vertical, please bear with me. And these clasts also consist mostly of crystalline material. Okay, we've got actually an example here of a sandstone, but most of these are actually quartzite, metamorphic quartzite, gneiss, or schist. And a dropstone. Very good. So what does that tell us? A little bit about dropstones in the Cryogenian. Here are some dropstones, and they all belong to Cryogenian deposits of different ages, probably Sturtian age, if we use that term, from Brazil, Australia, Namibia, and the USA. This is another example from Death Valley. In the Cryogenian, we do not have gastroliths. We do not have meteorites that can produce these structures, particularly if they contain abundant stromatolites, and they're not rafted by tree roots. Therefore, Occam's razor suggests that they must be ice rafted. That's really important. A little bit more about dropstones. While you've got me started on dropstones, I think they're beautiful textures. You can also see in the cap carbonates, in some cap carbonates, not all I should emphasize, but in some, evidence for dropstones. And here is an example from the Rasthof Formation in Namibia. And basically, in thin section, these beautiful laminated patterns you can see, these are dollar lamanites. These are all carbonates. And yet the clasts you can see are clearly different. They're outsized. Some of them are composite structures. So up here, for example, we've got a little bit of sandstone. Also using Occam's razor. Again, this must apply to these post-glacial cap carbonates. If you find these dropstones inside them, that's also telling you that you've got the evidence for glaciers lingering around on the Earth's surface when the snowball Earth events are supposed to have already passed. Okay, so that's another little taste of a lockdown project from last year. So if people are interested, you can check that reference out. Back to our Death Valley section. Remember the bit I told you, we have the glacially dominated diamictites and the non-glacially dominated ones. I call these Alistostrome ones because they're completely different. And why do we say that? They're dominated by lots of dollar stone. You can see in the succession here, broken up bits, really angular, no striated clasts, no drop stones of this material. And moreover, you can map the structures really clearly. You can see big blocks that are up to 50 meters across here. In other ranges in Death Valley, you can find blocks that are up to 1 or 2 kilometers wide. So massive gravitational instabilities conspiring to build up this succession. Okay, so in reality, and this is just to show you, I won't try to bore you all with sedimentary logs. They never work very well in presentations like this. Just to show these 1, 2, 3, 4, 5 intervals of these Alistostrome dominated diamictites, and the lighter blue colors are what we think are the glacial ones. So from basin to basin, from place to place, where are the glacial cycles that we want to correlate? Which processes are more important? Which are representative in the rock record? That is a big question. So we're thinking about a model like this, with a glacier coming from the side. We've got some extensional tectonics going on, a crystalline basement here at the bottom that's mantled by carbonate deposits. And those carbonate deposits topple off, go down the slope, and end up in the basin as an Alistostrome down here in brown. Okay, all the while we've got material coming in through the glacial conveyor belt as glaciogenic debris flows, as ice rafted debris, giving us all our lovely little drop stones that we can see in the basin. Okay, going forward, we're out of the Cryogenian into the Ediacaran briefly. You see drop stones there too. We know how these form, so let's move on. Okay, what we find in the Ediacaran that we do not see by any way into the same quality in older rocks is amazing striated pavements. And we thought it would be cool to take a drone and to try and map some of these structures in China, in Pindingshan, and we'll show you a few pictures of that in a minute. This surface you can see here is a sandstone surface. We're looking down. A drone is looking down on the surface, and it's made of sandstone, and it's what's noticeable is all these amazing ridges and grooves. So the ice was flowing from left to right, and it's produced a glacially striated surface that is incredible in quality. And just a few pictures of that from Pindingshan, from the paper in geology. This is open access. The first paper in geology I'll show you today from 2019. And you see this amazing shiny surface. Basically, the striations are sealed in by this silica gel, probably. and this is very easily weathered and peels off, and then you remove that and it's very hard to see evidence for any striations on the surface. So it's an incredibly lucky thing that these things are preserved. And the structures look exquisitely preserved. They really look like they were produced in the last 10 years. If you compare these structures to what you see in the Alps, remembering that this surface is about 600 million years old, this is as good as it gets in the Precambrian. And you can start to see, if we look again, this is a picture from the drone. On the ground, you see things like this. We can start to map structures, striation-rich areas. These features are produced probably through a combination of glacial abrasion and meltwater. And some bits are richer in striations than others, but that's for another day, that's for another project, really. Okay, so a word about striated pavements. So keep doing these little reminders. These examples are Ediacara. Okay, the rocks I showed you before are way older. They belong to the Cryogenian, and in those older or Cryogenian Proterozoic rocks, firstly, there are no reliable Sturtian age striated pavements globally, as far as we are aware. The PhD project of Tom van Dyke is doing a great job of investigating this in places like Utah. There are very few Marinoan age striated pavements globally. So this is a problem of, is it a problem of preservation, representativeness, or is it a problem of depositional process? In other words, glaciers simply never were present, grinding over the surface in some places. Okay, very important questions to ask. We're still rattling through time. We're coming out of the Precambrian now, and we've landed in the Phanerozoic. And we're starting off with the first of our major Phanerozoic glaciations, aside, of course, from the late Paleozoic Ice Age. We have the Hanantian glaciation, or the late Ordovician glaciation. And this is a time where Africa was basically centered in very high latitudes. In this reconstruction, the South Pole is shown somewhere over here, I guess in Mauritania. And through lots and lots of people, including little bits of work from myself during PhD and other work, but majority through other people, because there have been loads of people working on this. People have been plotting up things like glacial valleys, glacial striations, and other glacial records in these bits are Europe that were once connected to parts of Europe connected to North Africa. And the whole thing continues off into Saudi Arabia and Jordan and into Turkey. And you also see other deposits down here in South Africa. So I'm going to show you something here that might make you unsettled, hopefully. Okay, this is an area where you've got lots, this looks like Tic Tacs. Remember Tic Tacs, the sweets when I was a child. In orange are the outcrop belts. So late Ordovician glacial deposits over very large places, but also very large gaps in between them. It's a discontinuous mosaic of information, but luckily within between those orange areas there are sedimentary basins that where there's a lot of oil exploration and gas exploration taking place. So it's a place where you can not only do outcrop geology, but you can also combine it really well with information from the oil industry, and we'll try and do that in the coming slides. Okay, why do I say that this is a glacial record that might make you feel uncomfortable? Well, because starting off somewhere like this, it has many aspects to it that are simply either preferentially preserved or simply not represented in younger or older records. For the first thing, this is a hill in the Kufra Basin. Going back to the last slide, it's down here somewhere. This is the place. That is more than 200 meters high, and this is largely what the glacial record looks like. It's predominantly sandy. It's dominated by sandstone. It's very heterogeneous, I should say. And people that are doing oil and gas exploration hate this because that means that there are places where the sand disappears, and it's very hard to predict how these sand bodies connect with one another. But that again is a talk for another day. If we look at these deposits closer up, you see stacked beds of sandstone, 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 sandstone. Where is the diamictite? Where are the dropstones? Where are the striated pavements? How do we know this is even glacial in the first place? If our alien was coming down and looking in the Sahara, going to the Ordovician, would this be seen as the representative record of glaciation on Earth? And would perhaps the Pleistocene or the Precambrian be seen as oddities? I don't know. You also see beautiful facies. The outcrops are spectacular. They are exposed in 3 dimensions. They're a sedimentologist's dream. And here's a lovely example of a mud chip conglomerate, a very poorly sorted deposit that you do see at the base of channelized successions. And you also see things that are now increasingly recognized as supercritical flow deposits. I am no expert on supercritical flow deposits. However, with luck, there is a new issue in sedimentology that talks about these things in some detail. But these are deposits that caused a lot of people to scratch their heads. Were these actually some kind of massive storms? Were they representing sustained flows? What was going on when we were looking at these deposits in the early 2000s? And yet, in the late Ordovician record, deposits like this are everywhere. Okay, and you can start to do sedimentary logs. Yeah, this comes from a decade ago actually. The last field work that we did in the Kufra Basin, and basically the logs just are a few kilometers apart from one another. All the blue represents is that it's predominantly sandstone. We see evidence for scour and channel. Well, we interpret that these contacts represent scour and incision. They're very sharp contacts with gravelly deposits and matrix supported conglomerates. And we can even try to correlate some of these over some areas. So one of the really interesting things about the late Ordovician is its record of channelization is incredible. And I'll show you better examples in a minute. The other thing that is unusual to many people, if they come from a background of looking at Pleistocene or modern glaciation, is that the record of the subglacial process in the Phanerozoic is predominantly one of soft sediment. So it's not the only record. There is evidence for hard bedrock striation in some places, but by and large, you see these soft sediment grooves. So imagine taking your fingers to sand on the beach and plowing your fingers through the sand, and that's what you can see here. And over the top, some nice, a nice example of a discordance with some glacial siltstones here. Okay, so these soft sediment striations are often not thought about, or soft sediment striated surfaces in the Pleistocene record. People think about the continuum of subglacial features, and these are really, really represented in the ancient record and hardly accounted for in the modern and Pleistocene. And Saudi Arabia is really the most incredible place on earth to look at these things. Here's Saeed Tafaif standing there when he was doing his MSc with me a few years ago, and looking at these incredible striations, soft sediment striations. Another chapter entirely is to think about mapping things on a bigger scale. We're not going to do that today. Again, that's something that is out of scope, but you can basically get up and look in on satellite imagery and map structures that are possibly self-similar over huge tracts of desert, particularly in the Sahara. Okay, so coming back to the basics, how do you know, of course, that this is glacial and not some kind of slide, not some kind of later structure? Well, you find these amazing striated pebbles lying around in the desert, and you find faceted quartz. You find the striations that really resemble the sorts of structures we saw on the Ediacaran striated pavement, just at a very small scale on these pebbles. So we're really confident that there was glaciation, but the record is somewhat different. The other thing that is perhaps skewed in the late Ordovician record is that of tunnel valleys. These things are basically finger-like over-deepenings or valleys that form under an ice sheet. And the idea is that these are thought to be structures that form under really great pressure. So the meltwater is really greatly pressurized, and that means it can flow up and down over against gravity in some places. And I'll show you evidence for that in a minute. So we recognize these from the Pleistocene, but perhaps their greatest record is in the late Ordovician, because we can see them at outcrop, and the outcrops are really common. And here's an example from Saudi Arabia. This is the Arabian Shield, and the examples that I showed you, the outcrops, were somewhere around here before. But they really radiate around the shield, and the idea is that they tell you something about the direction of ice flow and also meltwater release. Amazingly, you can also see these things at 3 kilometers beneath the Earth's surface in Libya. This is from the paper of Smart in 2000, and this is from seismic data. So beneath the sands of North Africa, you see evidence for tunnel valleys, like you see in the Pleistocene. Here's an example of a tunnel valley from the North Sea, from Bradwell et al. In 2008, just to show you the bottom of the valley goes up and it goes down again. And the reason for this is that you require these to form beneath the ice through pressurized meltwater. If you're looking in the Pleistocene, if you want to work with Pleistocene data, you can do it with tunnel valleys. But like I said, the majority of them are in the subsurface. And you can use things like this, well logs. There's a very nice paper a few years ago by Janssen et al., 2013. And you can see probably the struggles that these people had to try and connect the facies between the wells. Very complicated, very heterogeneous, a lot of head scratching, a lot of uncertainty with regards to the way that these deposits connect with one another. Whereas if you go into North Africa, you can go and see this at outcrop. And firstly, this is from the dark days of my, very, very nice days of my PhD, which has basically this dipping surface. This is the base of a valley, and there's flexural deformation beneath the valley, telling us that something must have loaded it in order for the valley to form. What's more is that at the contact here, we find evidence for soft sediment striations, like we've already seen, and the fill to the valley basically onlaps in a very undisturbed way against the valley margin. Okay, so these things are really amazing examples in North Africa, perhaps the best examples of tunnel valleys that we have. More examples of these. Here's one from the Tassili Niger, just over the border in Algeria. And again, you can see these layers of rock here. These are basically pre-glacial sediments, and yet they're folded a bit right here at the contact, because the ice has loaded it. It's then cut this very sharp contact, and then you can see that the overlying deposits are basically massive sands and diamictites. So this is one of the things that we see, I emphasize repeatedly, everywhere in, well, obviously there are places between the valleys where there aren't valleys, but over a very wide area, valley systems like this in the Ordovician. Okay. On to the final chapter of today. we're going up again into the stratigraphy, and we've landed around about 300 million years. So we've fast forwarded about 140 million years since the Late Ordovician glaciation, and we're somewhere at the end of the Carboniferous, beginning of the Permian. And again, this is a time when ice sheets grew over big continents. Again, Gondwana, supercontinent of Gondwana. But things have shifted a little bit here, and we've started to have a subduction zone developing here in Western South America. And the general picture is one of migration of ice centers in a very general way from the Cordillera over here through into South Africa, and eventually ending up in Australia during the early Permian, okay, via, I should say, a period of time when ice was also active in the Middle East. So we're going to have a look at some examples from the classic sections down here in Southern Africa, where we've been working, and I'll show you some nice pictures, hopefully. So we're going into the so-called late Paleozoic Ice Age. This is a time that is a classic ice age. It was instrumental thinking about the early models of continental drift, the fact that diamictites match up on either side of the Atlantic, respectively conjugate margins, places like Namibia and the relevant margins in Brazil, and the fact that these things just connect up. The ice flow directions connect up, and everything connects up really nicely. In the late Carboniferous, we had a pattern of possibly ice flow from Antarctica. We had a pattern of ice flow from the north, from the Cryogenian highlands, and basically these ice flows are thought to have combined and then flowed westwards towards South America. But there's a lot of complexity, there's a lot of debate, and there are a lot of attempts to date with precision the timing of each of these glacial phases, because there are a lot of conflicting ice flow orientations in different places, okay? But this is basically, if I was to take one simple picture from the late Paleozoic Ice Age, this is one that I would show, and that is a classic diamictite, more or less like a lithified version of what we saw in the Austrian Alps, with striated boulders everywhere. These are very rare in the Precambrian record. They're very rare in the Ordovician, and yet they are ubiquitous in the late Paleozoic. If you look in places like in the Karoo Basin towards its western part, in Namibia, all across Namibia from the north to south, if you go to Oman, if you go to South Australia, and you just spend enough time looking around, you will find evidence for scratched and striated boulders and pebbles. So that is the message. And you see in this image at the bottom, this topography represents a very continuous sequence of diamictites, very stratiform. So diamictite is your dominant thing in the late Paleozoic, at least in this part of the world. And we're also coming to a place where we have fabulous, wait for it, yet again, soft sediment striated pavements. And here is another example, the second of the geology papers that we did in 2019, that looks at the origins of this surface in a place called Oorlogskloof in South Africa. And it's really accessible. If you're driving near Calvinia on a holiday, you just stop your car by the side of the road. There's a nice little inscription here telling you what it's all about. So you don't even have to read this paper. You can go and check out the explanations there on the ground, and look at these structures. So how do these things form? Again, looking from the drone, this is the direction that the ice was moving from. In the background, there's an outcrop of diamictite lying above. And just to emphasize, yet again, these are soft sediment features dominant in the Paleozoic record. And we see these lobes that clearly overstep, cross-cutting the previously formed features. And they look to all the world, when you look along them, in this picture on the right, like a little bayada, like little alluvial fans that you would see in Death Valley, coalescing at the base of a mountain range, flowing down into the grooves, like so. So what this tells us is that there must have been these things were not forming in a simple way. They're not forming through one simple event. There's obviously a little bit of cross-cutting that we need to explain. More on that in a minute. We see that these things are often bent and folded. That's not surprising. It confirms that they're formed in soft sediments. We also see things like deformation bands inside. We see structures like flutes, again, produced mostly in this case in a sandy diamictite. And we have these features here that basically, at a larger scale, fold and flex and deform and bulge the substrate. Okay, there's this sort of folding structure you can see here in the top diagram. Okay, so we need to explain this. If this is the case, and if there are then striations that come over here that are not deformed, then this pavement forms through a complex multi-stage process. All right. In fact, we get better information from this the more we spend time walking around, just admiring the features. Here is this set of lobes coming down. I mentioned before, flowing down towards the left into the groove, concealing very nicely the earlier formed striations. And yet you also see that there are scratches which are cross-cutting the surface at the top here. So, so these structures, these lobes that you see, were not just formed once the ice had melted back. There was something else that then happened to produce further grooves and striations. Okay. Big problem with the ancient record. In some cases, it can be fragmentary. And this is an important point, not to overemphasize the data. You could, for example, imagine that there is an iceberg floating around. So an iceberg happily grounding, bouncing down on the seafloor would scratch and striate parts of the seafloor like this. And this is certainly the case. The work of Fernando Vesely and others in Brazil has shown this. But in this particular case, we think that there's a little bit more at work, and I'll explain why. When you get your drone up into the air, you can start to map packages of cross-cutting relationships. And the take-home message here is that there are three colors. The yellow one is the earliest formed features. The orange one is formed as an intermediate stage. And then as a third stage, the green features, package 3, formed. And we've already seen evidence for this frontal bulge, the contact between 2 and 3 here at the bottom. And we can plot the orientation of each of these structures and map them. We're obviously in the field on the ground here, able to check things very nicely. And you can see these cross-cutting relationships. So this we found quite exciting because it told us that each of these striations, each of these families of striations or packages represents a separate phase. So what you might originally have thought of as a nice unconformity is actually concealing stratigraphy. So these surfaces mustn't be seen as missing time, rather that they can actually, if you look carefully enough, reveal information about sedimentary processes. This is what we think has happened here. We had a first phase here. Here's the glacier coming across the surface, and it's produced our first set of flutes and soft sediment striations. Here are the lobes coming down, flopping down into the gullies in between the ridges. And then perhaps a little bit of relative sea level rise, or in fact there's no sea level here at all, but base level rise. And the deposition of this orange package and striation and deformation and bulldozing in this region. So if you start to get a transgression, marine transgression, you'll lift the glacier off the surface, and that will cause it to touch down again, especially if there are tides at work in the background. And then a phase of renewed grounding, renewed incision. The locus of erosion moves towards the left, and then ultimately what you're left with today are these sets of three cross-cutting packages that we interpret as three phases of incision. So the message is that these so-called unconformities actually preserve information. That is the key thing, and you don't often see that. You don't often see this aspect of subglacial processes in younger records. Final slide before I wrap up, just to again once more emphasize the late Paleozoic Ice Age record. It really does look very much like the Quaternary. If you go to look at a typical Quaternary deposit, you'll see diamictons, you'll see outsized clasts, they'll be striated. Sometimes you'll see stratified intervals. Sometimes you'll see intervals with finer grain deposits in between. There are very close analogues to be drawn in this case between these two ice ages, I would say. Good. Not sure why this has come in a different order. I'll just wrap this up here. Basically, we thought about the modern and Pleistocene glacial deposits at the beginning, because this is something that we're most familiar with. We can go up to a glacier today, we can touch it, we can see what happens in front of it. The Pleistocene is common to many of us. It's in many of our back gardens, quite literally, or in our coastlines if we're living in Northern Europe. And it's dominated by diamicton, if we make a sweeping generalization. If we go back to the Cryogenian, we can also observe many, many diamictites, but we've been able to demonstrate, and many others have also demonstrated, that lots of those diamictites are non-glacial in origin. So you've got to be very careful, and it's very fashionable for many people to come along and say, aha, here's a diamictite in the Cryogenian, it must be glacial. In the Cryogenian, the striated pavements are very rare, and many of them are questionable. Whereas, if you fast forward, maybe 100 million years into the Ediacaran, we can find pristine striated pavements that look just like their modern day counterparts. Fast forwarding again through time to 443 million years ago, we see things like tunnel valleys, sandstone dominated sequences, soft sediment striated surfaces, and that is the dominant signature of the late Ordovician, which perhaps our little alien might take home and say is typical of the glacial record on Earth. The Carboniferous Permian also contains these striated surfaces, but I've also tried to emphasize that there are lots of diamictites there, and these perhaps represent the glacial record more closely than any other when we make comparisons to the Quaternary. So in a nutshell, I hope this has made you feel a little bit hopefully not uncomfortable, but that there are questions. What is really representative on Earth? Is the present the key to the past? And where do we stop with this when we think about the great debate next week? What do we take to our alien? And yeah, that's all from me for today. Thank you.
Thank you very much, Dan. That was a great presentation. I was surely very interested as a non-glacial person. I found it very informative. So everybody, please use the chat now to enter any questions that you might have for Dan, and we can get to them. Make sure and send it to everybody instead of just SEDS Online. If you send it only to SEDS Online, we won't be able to see it. And we always like to know where you're coming from. So please let us know where you're sitting and watching this webinar. All right, so Dan, let's get started. Our first question is from Owen, and he says, thanks for that comprehensive overview. We saw lots of evidence for glacial loading. Why does the evidence for unloading and the reorganization of sedimentary systems seem to be lower in abundance?
That's a great question. Hi, Owen. I think this is Owen Sutcliffe.
Yep.
I think that's a really important point. I haven't really even touched on reworking and things like isostatic rebound at all today. I can only imagine that we're looking. What I tried to do was I tried to provide what I hope was a balanced overview of these different records. That's not to say that I wasn't biased in the way that I did it, by trying to emphasize the things that we see repeatedly, or at least the things that I've seen repeatedly in the field. I mean, the deformation story is really well developed in the Quaternary record. Places like West Denmark, these classic glacier tectonized sections, the sections in Norfolk in the UK, and it's just really amazing. And whereas if you go to the Cryogenian record, I could be wrong. Obviously, I haven't seen every section. It would be really ridiculous of me to suggest that I had. I haven't seen anything that resembles those structures in any basin that we've been working in. In the Late Ordovician record, well, as you know, also in Libya there are a large, deformation structures too, and quite whether some of these are, always to do with glacier tectonism or later gravitational reorganization. I think we will always have debates about this until we've got good stratigraphic contacts that we can find at outcrop. Hope that answered your question.
Yeah. Our next comment is from another Owen, Amanda Owen. Great talk, Dan. Great to see lots of pictures from field work around the world. I also agree. Very nice to sort of virtually travel right now. Our next one is from Val, coming from Oslo. He says, fantastic talk, Dan. And can we all appreciate the mad amounts of class in the logs of your 2017 article? My question for you is, can you infer anything about the type and size of glaciers that prevailed at the time from the preserved structures?
That's hard. That's very difficult. I think in order to do that, I would like to step back and look at a satellite image, which I haven't done, because otherwise we'd be here till 9 o'clock tonight. Mm-hmm. Because at the satellite image scale, you can start to map really big things. You can start to see in the Ordovician and in the particularly in the Late Carboniferous, probably the best record I've ever seen of large-scale structures. If you think of the soft sediment striations scaled up to landscape scale, perhaps you get mega-scale glacial lineations produced beneath ice streams, and you can map these, and you can start to calculate on the basis of how densely these are packed and how they're organized over a region, the sort of ice flux that's required to generate them. And so by using features like this, so the bigger scale, you can then start to place minimum, maximum scenarios on ice sheet extent. But I'd have my reservations for doing that at the outcrop scale, with one caveat, and that is look at the composition of the stones. So if you look in the Diamictites and see that there are, for example, in the late Paleozoic Ice Age deposits of southern Namibia, Marienthal area, you see wonderfully diverse pebbles in the Diamictites, and you can see that they've traveled from huge distances. So you've got, in addition to the sorts of provenance analyses that somebody might do looking at sandstones, you can do the same by looking at pebbles and finding out where the source was. So you can use those sorts of proxies and think, well, how think of the glacier sort of hugging the landscape and collecting all these pebbles and bringing them to one place. So you could do it in that way, but I think that's a very broad brush approach.
Makes sense. Okay, our next question is from Sarah Giles from Columbia in New York City. Very cool talk. Would we expect variations in the types or structures of glacial deposits depending on the latitude of glaciation? I'm thinking of the Proterozoic glacials that are suggested to have formed at lower latitudes.
Yeah, that's an interesting one. I would suggest that Yeah, I mean, this is part of the problem of the ancient record in a way. Obviously, I've perhaps tried to see the positives in these different outcrops. If I start off with the late Ordovician or the late Carboniferous ones, we know pretty well where the South Pole was at the time, and we can relate the deposits to that. What you can see in those records, which is really, really instructive, is that the further you go away from the center of glaciation, if you basically count up this in the stratigraphy, how many phases of subglacial deposits you have, so soft sediment striations, generally the further away you go, the fewer you get, which makes sense, meaning that at the maximum extent, the ice only got there once and then retreated back in a kind of a pulsed way. When you go into the Cryogenian, you just can't do that because like I tried to emphasize, most of the sections, with some exceptions again in places like Mauritania in the Neoproterozoic, where you do see striated surfaces, you just don't have those. You don't have the geomorphological evidence to do it, and you only see the basin. And that is the terrible problem. So we're only able to look at things like the overall architecture of the sequence. If things are coarsening upwards, does this tell us something about the ice kind of getting closer, or how does it work out? So we're trying to do our interpretation in a slightly restricted way when we're looking at those Cryogenian deposits.
Yeah.
Not sure if I fully answered that question, did I?
I think you got to most of it, yeah. If you have any other further follow-up questions, Sarah, just make sure and send them to the chat and we'll get to it. All right, our next comment is from Christopher Kettler, just says, thanks, Dan, great talking, beautiful locations. Jonathan Osmond wants to know where the comments go if you send to SEDS online. So I'll just quickly address this, we don't usually talk about it. What most people don't realize is that there's a bunch of us SEDS online organizers in the background here. So although I'm reading out the questions, my account is under my name, Chelsea Pedersen, and somebody else has the SEDS Online account going in the background. So they're not the ones answering the questions, which is why I won't ever see them and be able to read them. So that's why we just ask you to please send to everybody. All right, so our next question is from Christy Rowe. Hi, Dan. I've worked a little on the giant load casts in the Ordovician and the Cape Fold Belt. Your photo of folds from Norfolk actually looked quite similar with the overturned edges. Any thoughts on how to untangle the contributions of fluid escape versus shear loading in structures like these?
Yeah, okay, thanks, Chrissy. It's a good question. I'm aware of the debate regarding the fold zone in the in South Africa and the Snoekop member. I think, yeah, I mean, yeah, this is a problem. I know that we've got the loading versus, you know, if you've got some kind of subglacial shearing going on. I would prefer to look at those sections in more detail and to, you know, maybe get some three-dimensional images of them. But I don't know. I really don't know. I've always been very uncertain about the origins of those. I've seen them in passing in the field, just very briefly, but yeah, it doesn't really help, does it? I'm not really helping at all.
Maybe, Christy, if you have additional...
Happy to answer a question offline if you want to.
Yeah, I was just going to say, Christy, go ahead and email Dan if you have more questions, or if you want to send him any further data that you might have, and I'm sure he would be able to better answer that question for you. Our next question is from Abdullah, watching from Saudi Arabia. Thanks so much, Dr. Daniel. How to recognize the diamictites in the subsurface cores, and is there any way to recommend, are there any recommendations to classify different types of diamictites?
Right, okay, so the first thing I would say is there are lots of techniques available. It's important to know what you were trying to do, okay? And I think that, you know, in our group, Christoph Kettler, who's already asked the question, is working very intensely on this in terms of trying to extract fabrics from the diamictites. And that means detailed photogrammetry, dovetailed with quantitative fabric analysis that can be done, and it can be done at a small scale, and basically possibly also in core. What I would suggest is, knowing a little bit about the diamictites will tell you a bit about perhaps flow direction. And we had a very nice discussion with Emrys Phillips about this the other day. It's not really at a stage where we can probably tell if a diamictite is glacial or not, so I don't want to disappoint you, but you may be able to say something about the flow direction of what looks to be a massive deposit by doing careful analysis of the orientation of the clasts. So we're able to, again, this is out of scope of today's talk, to extract information, statistically meaningful fabric information from diamictites that look completely massive to the naked eye. So there are ways to really get into this topic and to do it in detail. But unfortunately, I couldn't touch on that today.
There's only so much time. Yeah.
Yeah.
All right. Our next question is from Marik from Krakow. Great talk, Dan. Thank you. About diamictites as the texture in the Central African belt. There are syn rift and syn orogenic olivestromes, and some that you have shown, strangely interpreted by many other people as tectonic friction breccias, in spite of no tectonic features. And then the cryogenian, glaciogenic sediments, no doubt in many boreholes, but several occurrences as debris flows with no glaciogenic indicators at all.
Yeah, indeed. I mean, I've just sort of that was more of a comment.
More of a comment, I think, than question. Yep.
Yeah, I mean, I think that's certainly borne out by the work of people like Kirsten Kennedy for her PhD in the Congo Basin and looking at those boreholes. One of the recent papers published in Sedimentology, I think, on that. And it just, if nothing else, I think it's nice that you've made that comment, because it emphasizes to people, if you were approaching other glacial records, then you wouldn't rush in and say that is a glacial deposit. But for some strange reason, when people start to look at the Cryogenian, they seem to lose control of their senses sometimes and say, yeah, that's definitely of glacial origin. So yeah, if there's anything I would say, it's a lesson of being very circumspect about the evidence and looking at the context. If you can't find all of this wonderful richness of information that we have in the Ediacara and all the Paleozoic records, really.
Definitely. I'm going to throw in one of my questions, because it sort of tailspins off of this one, let's say. So you talked a little bit about how to distinguish glacial and tectonic diamictites and the different types of textural features that might be present in one versus the other. I naturally go a little bit more towards the geochemical proxies. And so I'm wondering if you can distinguish between the two types of diamictites, or between those two, at least, let's say, based on any geochemical characteristics.
Yeah, I would say most definitely in the example I gave in Death Valley, which is only one very small Death Valley belt. This is another thing. You've got to be very careful about what is representative, what sections you take as representative. So this very small section, or 1.4 kilometers thick in Silurian Hills, is just one section in Death Valley, and you can go to other outcrop belts and see different things. A different sequence architecture with different number of elastistromes and different number of glacial deposits. And I would imagine that in this local area, the glacial deposits would have more of a bedrock character, whereas you'd probably have more carbonate within the highly ground up matrix of the elastostrome. But the problem is, because you have to think about those processes on quite a local level. It's common for people to say, in this section in Death Valley we see such and such a thing. My point is that you can see it in some places, but not in other places in this outcrop area. You might have a completely different signature, and you might think, well, actually the glacial deposits are much richer in carbonate than in the sections I showed. So I'm always mindful of the outcrop context to these deposits first, getting that right, and then really getting to grips with the geochemistry once we're happy about the outcrop relationships.
Yeah, that makes sense. Okay, Christy Rowe is just letting you know that she's coming from McGill University in Montreal, so in case she reaches out, I think.
Of course, yeah, great.
So Steve from North Wales has our next question. Great talk, Dan. Your Alpine striations on gneiss rocks look pristine. In the far north of Scotland, the Lewison gneiss, which was glaciated only 15 to 20,000 years ago, doesn't really show anything like your examples. Do you have any ideas why?
Yes, I do. And the reason is, well, I like this paper very much, but not everybody seems to. There's a beautiful paper published in Geology by Simontoff et al. In 2017 that were looking at Yosemite and Yosemite National Park in the US that was glaciated during the Pleistocene. And you can see that there was this shiny surface, okay? The shiny surface they interpreted as being precipitated, representing a silica gel, a very thin layer, like a nail varnish that seals in the striations. And once you start to peel this away, you can see this in lots of different places. You basically lose the evidence for the scratches. So those striations are only skin deep, so to say. You're really only scratching the surface. You peel those things away and you've lost already an important part of the record. And so I think that it depends partly on whether this shiny surface is preserved. I think many people will remember this if they go and see next time, see if there's a shiny sort of surface to the striations. But it also depends on the lithology. So, you know, rocks that are pretty, I'm sort of thinking about, you know, go to Laxford Bridge or something like that, and you see really sort of mixed assemblages, you know, they're going to have a very different preservation to these striations than you would if you look at a sandstone that's much more homogeneous. So it depends on the bedrock as well.
Yep. Okay, our next question is from Danielle from Switzerland, our current president of our official sponsor. So thank you for joining us today. He says, great talk, Dan. The pebbles and the carbonates of some of the Neoproterozoic records are quite puzzling. How often have you seen them, and what are your thoughts about their presence?
Yeah, well, I've seen them once in Namibia, hence including these in the presentation. But I am also hearing that there are similar structures preserved in the Nantua Formation in China, and they seem to be, well, if people would like to think that there are Sturtian glaciations that are global, those glaciations might match up, and so I'd love to see more examples of them. But by the same token, looking very carefully at the texture. So just pebbles floating around at the bottom may easily be explained as a transgressive lag, and then perhaps a little bit of carbonate reworking if these are embedded in the matrix. But I'd really like to see lots and lots of delicate laminations and the dropstones. Oops, I said the word dropstone. The lone stones, which I interpret as dropstones, occurring at lots of different levels. So the more levels, the better. The more examples, the better. If people have more examples of these, I'd love to see them because I think it's a really, really exciting phenomenon.
Definitely. So you heard him, folks. Send him your photos. Our next question is from Christina from Durham. Hi, Daniel. Thank you for the great talk and intriguing photos. What is the difference between striation of soft sediments in the pre-quaternary record as opposed to soft sediment deformation and fluting in the quaternary record?
Right. Okay. This is a good question. Fluting, or development of fluted terrain, fluted glacier fall fields, seems to be really well described, and everybody knows about these things in the quaternary. However, these structures are almost exclusively developed in diamictite. When you go back into the Paleozoic record, hopefully I've convinced you that there is a lot of sand around. And some of this might be to do with the fact that there was simply a lot of sand lying around before ice sheets expanded over the surface and cannibalized the material. So you've got to think that actually this material is much finer. It can preserve structures to a greater degree of fidelity, maybe, than you can a very bouldery diamicton, where you can just about see the coarse scale structure. So I think it's an advantage of having these sandstones in the older deposits that allows us to see these finer structures. I think that you simply don't see them in many modern glacier forefields because the material is too coarse. You simply can't get those small scale structures forming.
Yeah.
And that's it. So I think it's an interesting little thing that maybe should be considered as the ultimate end member of the series of subglacial bed forms, if we want to consider the entirety of Earth's glacial record when we think about processes.
Yeah. Okay, our next question is a follow-up question from Val. I have a follow-up, he has a follow-up question while thanking you for your first answer. Going back to the structures versus the types of glaciers, is there a relationship between the type of structures or deposits and the thermal regime of the glacier?
Yeah, good question. We possibly, yes, possibly. One of the problems we are getting again is if you're thinking about some records, the Late Ordovician springs to mind again and again, is we seem to have a very meltwater dominated record with things like the tunnel valleys, which record obviously a major meltwater episode. We could start to think about things like, you could speculate that areas where there is no evidence for subglacial plucking, abrasion, where there are poorly developed surfaces, you could speculate that these are cold-based regions. You know, this would work quite well to explain, if you want to push it in this direction, the absence of structures in the Cryogenian, although I would never recommend that the absence of structures is used to support a hypothesis. And then, yeah, I mean, we get glimpses of it. So the examples I showed from China, from Pingdingshan in the central China origin, do have these beautiful P forms, yeah, these scoop-shaped structures. And we think when we see these things, they represent quite a lot of meltwater at the base as the striations are forming. So this is telling us that we're dealing with probably a temperate to polythermal regime at the base of the glacier in that place. But wouldn't it be nice to be able to do that over wider areas?
Absolutely. Okay, our next question comes from Marcello from Bremen. Great talk, Dan. You already mentioned that was a tricky outcrop, but do you have any thoughts about the process forming the sandstone with high flow regime structure in the glacial setting?
Yeah. Okay. So yeah, I do. These successions form. Well, I showed the photo of these stacked sandstones. You know, the sandstone intervals are beds, poorly developed, but about 5 meters or so thick, and you see these things stacked one on top of the other. And these structures form part of a sequence of features that Guillen et al. Described as climbing dunes in 2010 in sedimentology. Sorry. And generally interpreted to be sustained, maybe glacial outburst deposits. Simply, you know, things like the continual climbing structure that you see, all sorts of features that I don't personally fully understand, but people talk about shoot and pull structures and, you know, all of these other things, one on top of the other with very poorly developed bed boundaries, telling us that we have fairly sustained flow. Yeah, I think that's basically it in a nutshell. Probably sustained flow, probably possible outburst events in some places.
Okay, our next question comes from Mohammed. Great talk, Dan. I'm working on in the Egyptian desert, and I'd like to ask you about the preservation of large-scale landscapes, for example, U-shaped valleys. And he would like to reach out to you after the meeting.
Yeah, I'd love to do that. Thank you. Yeah, I'll try and help you as much as I can.
Yeah, so just grab his email from online, and yeah, you can reach out to him with any further questions. Okay, perfect. Yeah, so lots of nice comments there at the end. Danielle says, thank you. Again, your talk has been a great introduction for the first SEDS Online Great Debate. And I will second that. That was a perfect sort of intro and start getting all of our brains thinking and tingling about what the modern might mean for the ancient and what the ancient might mean in comparison to the modern. So you guys don't forget to join us next week is when we'll have our first birthday and celebrate by having this first SEDS Online Great Debate. And we look forward to seeing you then. Dan, thank you again.
Thank you very much for inviting me.